So let's go ahead and get started. So this is the semi-plenary session this afternoon. Thank you for cutting your lunch break a little bit short to attend this. I'm Irina Tazar. I'll be chairing the session. So it's really my honor and privilege to introduce this afternoon's semi-plenary speaker, Professor Vipin Kumar. Professor Kumar is a Regents Professor and holds the William Norris Chair in the Department of Computer Science and Engineering at the University of Minnesota. His research spans a variety of fields. It includes data mining and high-performance computing, as well as other applications in climate, ecosystems, and healthcare. And the research has resulted in the development of the concept of an ISO efficiency metric for evaluating the scalability of parallel algorithms, as well as some highly efficient parallel algorithms and software for sparse matrix factorization and graph partitioning. And so if you've worked with Metis or ParMetis, those are some of the software that have those algorithms. Professor Kumar has authored over 400 research articles and co-edited or co-authored 11 books, including 2 widely used textbooks, Introduction to Parallel Computing and Introduction to Data Mining. And very recently, he's edited the collection entitled Knowledge-Guided Machine Learning. Currently, Professor Kumar's major research focus is on knowledge-guided machine learning and its applications to understanding the impact of human-induced changes in the Earth and its environment, where some years back he served as the lead PI of a 5-year, $10 million project on the topic entitled Understanding Climate Change, a Data-Driven Approach, funded by the NSF. And so finally, Professor Kumar is the recipient of many awards and accolades. I'll just mention a few of them. So he has been elected a fellow of the Association for Advancement of Artificial Intelligence, the American Association for Advancement for Science, the Association for Computing Machinery, IEEE, and SIAM. And Professor Kumar's foundational research in data mining in HPC has been honored by several awards, including the ACM SIG KDD 2012 Innovation Award, the 2016 IEEE Computer Society Sydney Fernbach Award, and more recently, the Test of Time Award from the 2021 Supercomputing Conference. And so with that, I'll hand it over to Professor Kumar to give his presentation.
Thank you, Rina. It's a pleasure to be here. So the talk is about AI meets science, and of course, we are living in the age of AI revolution. It's poised to fundamentally change how we do things. And if anybody had his doubts about this, it probably got cleared up about 2.5 years ago when ChatGPT came out. And soon after that, last November, 2 of the awards, Nobel Prizes for chemistry and physics, were given to it, right? So what I like to remind people here is that this revolution didn't happen overnight. It didn't start with ChatGPT. It actually is at the confluence of 3 different areas: the data that has been growing, computing that has been becoming more and more powerful, and algorithms that have become smarter and smarter over a period of time, right? So this revolution has been brewing for literally 7 decades. The term AI, the artificial intelligence, was coined exactly 70 years ago in 1955. Okay? Although the work that's being done in this area has changed its shape, a lot of different things got done along the way with different names. And the deep learning revolution, which is sort of changing everything around us, also started in the 50s, about 70 years ago, but came from a different thread completely. The people in the brain-inspired computing would not call themselves working on AI and vice versa at that time. But of course, everybody's mixed up together. And 1957 is when the first elements of what you're using today in terms of deep learning sort of came about, perceptron, and again, this is a long journey. So this area, this big journey that sort of started almost 7 decades ago, has been sort of changing its name and shape and what sort of got done over a period of time. And they were having many ups and downs along the way. And more recently, in 2012, we can sort of say that age, the second age, I would sort of call it, came to sort of to a major point by having the White House, the Obama White House in 2012 declaring the big data initiative. Some of you may remember it. It was a big fanfare. It sort of came about just about a year after McKinsey issued a report that being able to analyze large data sets properly could literally add trillions of dollars of efficiencies to the economy, and it sort of launched its own sort of life to it. If you open up on the web the initiative's announcement, and I attended the 3 workshops that were held at the White House Conference Center right after that in successive years, there was no mention of AI at that time. It was only about analytics and big data, right? But the kinds of things we're doing today is sort of a continuation of what happened there. Okay? 2012 is also the time where this new generation of development that started happening, one after the other, and it brought us here. It brought us to ChatGPT, and it brought us to this conference where I noticed almost half the talks mentioned something about machine learning, right? So it's a complete transformation. So what happened in the last 12 years, 13 years? And I'm mentioning them to you just to show you that how quickly the excellent things have been happening over the last 70 years, but how quickly things are happening now, what the rate of discovery is actually increasing. So we are sort of at an inflection point, right? 2012 was the first time the AlexNet wins ImageNet challenge. And that is important because for almost 30 years, remember in 2012 we have the big data initiative. It has nothing to do not only with AI, but also nothing to do with neural networks. Right? Neural networks were left isolated for almost 30 years. Nobody really paid attention to them. Right? So that's the first time somebody was able to show, Jeffrey Hinton and his student was able to show that the techniques developed in 1989, the convolution neural networks, and the ImageNet data set, which was built by the big data community that sort of sits in the middle, together with advances in computing. NVIDIA chips were still good at that time. The students paid money from their own pocket to buy some NVIDIA chips, the GPUs to run the AlexNet, right? Was able to show that they were able to make some improvements on the standard benchmark. That was the first thing that sort of turned around people that look, what is happening for the last 30 years, there is something to pay attention to it. And then things started happening very quickly in succession. 2016, the translation became suddenly much better because in 2013, a new methodology got developed, of course, self-supervision. I'll talk to you about that. 2016 is also the time AlphaGo beat the Go champion, the world champion, very complex game. And 2018 is when AlphaFold solved protein folding, a very long-standing problem. So you can sort of see these things coming one after the other very, very quickly. This is all before the ChatGPT showed up, right? Okay? And these all are extremely important problems, very difficult problems that people were sort of working along for a long time. So ImageNet, imaging, being able to recognize object in an image, was a long-standing problem. It dates back to the beginning of AI, and it was very hard to sort of make progress on that thing, even after this big ImageNet data set was created. And this is when people realized, you could really do this much, much faster. Big development. The next one, the Google Translate translation, was a huge challenge. Even in the 70s, DARPA was funding these big projects for converting English to Russian and vice versa at the height of Cold War, and completely failing, and things started improving a little bit, but there was a dramatic jump in 2016, big problem. Okay? 2016, AlphaGo beating Go champion. I like to mention right after that, AlphaZero was used to create a chess champion in the world, and again, an extremely significant milestone. 1957, one of the founding fathers of computer science, Herbert Simon, made a prediction once the algorithm was written, alpha beta, that within 10 years, computers would be able to beat the world chess champion, right? The computers would be the chess champion. That was 1967 was the timeline. 67 came in, nothing happened. 70s came in. I was a student at that time, nothing happened. It took 40 years from 1957, 1997, for IBM to build a supercomputer and put a lot of resources to sort of have a deep blue computer beat for the first time a chess champion. Okay? Then 20 years later, in 2017, this entire thing got upended. So basically, in 97, what you sort of knew about, if I have a supercomputer and a lot of money to spend, I can play a game with you. And of course, if you get smarter, I'll have to put more money into it, right? The computer had to play 200 million moves a second and analyze them and have a lot of knowledge to it. In 2017, what happened was that a computer was so simply given the rules of the game. It played against itself and became quickly not only the champion, but it's such a dramatic improvement in performance that you learn from it. You can learn the strategies from this computer. So dramatic changes happen. And why all of these? What I'm telling you all of this? Because these were a dramatic jump in what we could do. Now, and there are multiple things that I like to mention here. One of them is that nobody anticipated any of these changes. Okay? Shortly after 2017, in 2017, the transformers were sort of designed. So that's sort of what led to the large language model and transformers and a lot of the generative AI revolution you're talking about. In 2018 and 2019, January, we met together, the AI community met together to create a 20-year roadmap for AI. Okay? And if you go back and read that 80-page report, you'll find no mention of the large language model. So we couldn't anticipate as a community as to what's coming just a year or two down the road, right? Okay? The other remarkable thing is that a lot of these development that you're seeing here in the last 12, 13 years are conceptual, are very easy to understand, and they're no magic. If anybody's thinking that the AGI is coming in, well, maybe it's coming in, but for any of these things to happen, actually they're all simple mathematical concepts that you learn and then you move on, right? The very first one, the AlexNet, the ability to build representation that can be refined to images, that thing was sort of running on since the 80s, and then of course it saw the light when the data and computing became big enough. The next one for the translation that really created a jump, okay, again was made possible by a lot of computing and a lot of data, was an extremely simple idea. Okay? So simple that you sort of say, hey, look, there is nothing in it, right? And what was the idea? It was about taking the words and converting them into a representation, to a vector. Okay? Because if you have to manipulate something on a computer, you got to have numbers, right? Okay? And you would want those numbers to have some meanings. Okay? And before this point in time, if people wanted to do translation, they are talking about looking at for the most part, much of the multiple decades of history, you're trying to understand the grammar, what is noun, what is pronoun, what is verb, how they come together to form a sentence. So you parse a sentence, you ascribe words to a meaning, and then you do the translation. Okay? Here, it was more like, well, let's take the words and convert them to numbers that really mean something. And how do you convert them? Well, let's take this deep neural network. By the time deep neural network with large computers became available, let's take any sentence and delete a word and try to predict it. That means if all of the words in the English dictionary had the right numbers, you will be able to feed them into a network and predict the number in the middle. So basically, it sort of gave some semantics to the numbers. All it's doing is capturing the regularity in the data. And how good did it become? It became so good that you can take the number for king, subtract the number for man, add the number for woman, and what do you get? Queen. So the representation became so good without doing anything, just by large data set, right? And again, the examples, of course, are abound. So amazingly simple ideas sort of were put together with a lot of computing, a lot of data, and made dramatic advances. How did the next advance happen, AlphaGo? It was combining deep learning with reinforcement learning, an idea that has been circulating for 30 years, going back to the 60s to 80s, right? It started from this problem-solving search planning methodology, and it became sort of a thread that was sort of sitting on the side, not being paid attention to. And that together with deep learning creates such powerful methodology that actually is why you sort of see the ChatGPT giving you such good results. It's not just the transformers, not just the large data, but also being able to reinforcement learning. And if you're trying to design new materials, again, those are the kinds of things in which that technology comes in plays an important role. Again, going on, the transformers again came about by improving this methodology for assigning vectors to the words. This was being done in the context of languages, so that the numbers you assign to them, the vector you assign to them, become sensitive to the context in which they operate in. Okay? So all of these things sort of came together. All of them have very relatively simple ideas, but they're extremely powerful. And then, of course, combining all of these things together, what brought you to ChatGPT, brought you to generative AI, and brought you terms like transformers or in-context learning and context-sensitive architecture that did not exist in our vocabulary just a few years ago. Right? So these are exciting times, and this also tells you as to what more may be coming in as we sort of look forward. So now, the other thing that I would like to sort of point out, that if you attended any of the machine learning talk in this conference, or for that matter, any machine learning related talk in any scientific discipline, you would find that people are using constructs and concepts and methods that have been built in the AI community, or the broadly speaking AI and deep learning community, where people were trying to solve problems in computer vision and languages. You're either trying to model a language or you're trying to understand an image, right? So literally everything you pick up, and I'll tell you, well, this is where the genealogy is, right? So there is an increasing feeling in the community that the next revolution in AI actually is going to be driven by a much wider class of scientific domains. The computer vision and language modeling are also scientific domain. Okay? And it will help us address some of the biggest gap in AI because being able to generalize to scenarios that have never been seen before is very critical if you're trying to solve a scientific problem. You can't just sort of say, look, it works, but it doesn't work all the time. And there are issues like being able to quantify uncertainty. Do you know, does the program know, does the machine know what it doesn't know, or how much does it know for sure, right? Can it explain what it does? So all sorts of things that are sort of swept by the side because you're working in languages, but working in translation. If a few things go wrong, it doesn't matter so much. So all of these challenges could be addressed. So there was a series of workshops that were held in the last 2 years. NSF had asked me to organize. One of them was held at the headquarters in Arlington, and the second one we held it at University of Minnesota. They're both NSF workshop, and it sort of came with a report, and there was a lot of discussion and a lot of consensus that yes, this is the new revolution has to be driven by the scientific community. So this is very exciting which is why it was very important for the people who are working in AI and people who are working in scientific problem to come together, because you're not only using what is being done in AI, but you have the potential to dramatically advance the state of the art in AI. Okay? So as we all know, there's a huge interest in AI in sciences, to the point that people are beginning to think, hey, are we looking at a post-theory scientific framework, in which case you don't need a theory, okay? Or will black box models make the process-based model obsolete? And somebody might get this impression if you look at things like the weather forecasting. Weather forecasting has been done using primarily the physics-based model. And today, actually all happened within the last 12 months, a number of machine learning-based models, the deep learning-based models have been built that actually beat the state-of-the-art process-based model. So one could sort of be forgiven to think like this, right? But it turns out that there is a big gap between what the science needs and what can be made available with the existing methodology. One is that a lot of the scientific problems require a lot of data. And the kind of data, you have a lot of data, but not the kind that could be used to build, train some of these models. So that's one part. That means some of the things that would work very well on the languages and vision may not work for scientific problems. They can generate physically inconsistent results, which means you already know there's something wrong with your result. It can't make sense. But much more important way of manifesting this is that they don't generalize to scenarios that have never been seen before. Okay? And in any case, if you are just able to predict without having any mechanistic understanding, it doesn't really advance the science, right? And of course, this is really critical because many decisions that involve physical and environmental systems impact the well-being of people, right? And the consequences of missing a prediction is much more serious here than perhaps in recommendation for a hotel or an image, right? Okay. So within that, what we have here is the dichotomy in which we have the traditional science-based models that are being built in the community, various communities, including the ones here, which sort of you take the phenomena, you model it using equations and maybe first principle-based methods, and then you use some amount of data to perhaps calibrate the models, but those models are never perfect because they are approximate. Okay? So you're looking for something different. And then you have these data science models that rely upon very large amounts of data. They look for regularity in the data. But because they can only look for regularity in the data they are used to train, they always have the risk of not being able to generalize to scenarios not seen before. Okay? So how do you sort of take this to the academies and then you bring them together? And this methodology of data science models that are guided by scientific knowledge is trying to fill this gap. Okay? And this idea sort of started coming to a lot of people. This been people have been thinking about it for quite some time. In our own group, we started thinking about it in 2014 when we published the first paper on the topic. And then the idea is that these, in scientific applications that are governed by laws of nature, there should be a way to infuse that information into the data science, right? So, and this general area, of course, is sometimes also called physics-guided, physics-informed, physics-aware, but this is this general body of work in which you are trying to guide these purely data-driven methods with scientific knowledge. Okay? And it's a rapidly growing community. There are lots of workshops and meetings. There's a book. There are survey articles. And it literally, you can find any field, any scientific field, and you will find people working at this area. It's picking up momentum, right? And if you look at the timeline of activity, I sort of put together a bunch of papers on this. To 2016 and earlier, there were only a few papers. Then 2017, 2 major papers got published. One was the theory-guided data science from our group, and then again, the precursor to the PINs that sort of got published in 2017. And then, and after that, you see this thread sort of being explored in many, many directions, including aquatic sciences, biology, agriculture, and of course, the computational mechanics and the communities that you see here. And there are lots of review papers and books that have come about. There are a lot of funding agencies that are interested in this general topic of AI science, and then a lot of different workshops that you sort of see that. So this is a very rich area that is being pursued very extensively by many, many segments of communities. And so if you sort of want, because this is an evolving area, and again, it is taking shape in itself. So this slide is trying to capture the entire sort of research that's happening and this intersection of scientific knowledge and machine learning along multiple dimensions. That is, what is the format in which the knowledge is represented? Is it PDEs, or scientific laws, or symmetries, or knowledge graphs, or mechanistic models? What kind of, is it the knowledge is perfect, or is it imperfect? How are you trying to integrate knowledge of science and machine learning? Is it centric to process-based models, or is it centric to machine learning? What are the different ways you're infusing knowledge inside a machine learning algorithm? Are you putting in the loss function? Are you designing an architecture? Are you pre-training the model? And again, the vast majority, and there's a huge number of use cases, which is, of course, an incomplete list here that I'm showing here. And just to illustrate a few things, if you sort of say, well, let's explore this dimension of format for using knowledge, if you have PDEs that fully represent your phenomena, and your objective is to be able to compute the PDE solution very quickly using perhaps a data-driven method, then PIN and the FNO, those are the kind of methods that are fit squarely right here. But on the other hand, if you have other kinds of scientific information like the laws, energy conservation, mass balance, symmetries, knowledge graphs, mechanistic models, you have other things that you could potentially do. Okay? If you have perfect and complete knowledge, again, then you capture it through a loss function. You come up with you build a neural network, you make a prediction for a solution, you check how far off it is from what you expect it to be in terms of the PDE, which is easy, and then you make a loss on it, and then you sort of go around it. Or if you have imperfect and partial model, then you got to do something different. Okay? You could be making it process-centric, that is the process that is supreme, but machine is only replacing a small piece of it. For example, the subgrid parameterization used very extensively. Or it could be ML-centric, in which the ML model is the supreme and it's just being modified by scientific knowledge. Or there are methods that can sort of combine both of these ideas, right? And again, last one, how do you actually bring the knowledge into the machine learning algorithm? It's a very rich area in which learning correspond to being able to design loss functions. And it's not just simply modifying the loss function. It could be balancing different losses that sort of relate to your application. Architecture means you're bringing in your understanding of the process and figuring out how do you architect the entire machine learning algorithm. And the pre-training part, of course, is extremely important, because pre-training is where you're bringing the known structure about the problem. And the structure could come from scientific simulation. Even though they have imperfect models, they could still be used to initiate the model. Or this is where the self-supervision comes in, that was so powerful for language translation and everything else that led us to the age of generative AI. And of course, there are many, many of these applications that you can sort of work with. Okay? So I am, I don't work in the area of computational mechanics, but a lot of my work is in the case of environmental sciences. And I'm just going to take a few minutes to give you a little sense of what this paradigm coming together has done to help addressing some of the environmental challenges. So if you're trying to model an environmental system, you are again building a model of a reality. The reality could be a field, could be a river catchment, it could be the area where you're trying to grow some food, and it's impacted. The environment is impacted by physical drivers like weather. The weather is generally the major driver. You may be interested in response. For example, you're trying to figure out how much water is going to flow in the river. Maybe you're trying to do flood prediction or drought prediction. You could be trying to measure the temperature of the river, because the temperature is the master variable that determines the health of the aquatic systems. You could be trying to predict the greenhouse gas emission from a farm, because you're trying to incentivize farmers to grow fruit in a way that it has a less impact on the carbon cycle, and perhaps they can participate in the carbon market. So if they can reduce the carbon impact, then maybe they could be paid by corporations who are trying to get to carbon neutral world, and then sort of the list goes on, right? The relationship between the response that you're interested in and the drivers that determine the response is determined also by the characteristic of the system. For example, what's the nature of the land, what is the quality of the soil, how are you managing the soil, and our practices and so forth, how much fertilizer you're putting in, or whether you're tilling the land, and all sorts of things like that. And then you also have observations that are coming in from the satellite that are not changing anything, but they are windows into the system, they serve as a surrogate for the information you may be looking at. And again, and you may be interested in forward models. That means you given the drivers and the characteristics, can you come up with the response? Or you may be interested in inverse modeling, in which you are given the drivers and response, and you're trying to figure out the characteristics of the system. Maybe you want to parameterize your model. Maybe you just want to figure out what the characteristics are, because that are of interest. If you're trying to pay somebody for following the right management practices, then you sort of say, hey, look, I want to figure out exactly what you're doing so I can pay you for supporting the environment, and so forth. So both forward modeling and inverse modeling are used, of course, in many, many scientific disciplines, including the environment. And in many cases, you may be interested in just improving the speed of the forward model. That means you want to do it much, much, much faster. But in a normative situation, oftentimes the PDEs that you use or the models that you use are actually quite imperfect. So you're not only interested just in speeding of the models, but you're also interested in improving the quality of the models by way of using data. So you could be potentially build a much better model using data. And of course, inverse model, of course, is always a hard problem in any discipline. And then the question is, could you do it better using machine learning? So again, I will give you just a quick primer on what it might be in hydrology. And again, some of you may already be working in areas like this. So if you're trying to build a model, a process-based model, which is the dominant way of computing in these areas, hydrology plays a central role in all of the environmental problem. You are trying to basically model the phenomena, and you're modeling different components of the environment that you're trying to predict the response of. So for example, there is a soil column here, and you're trying to figure out, well, the response of the weather to the rain, on the rainfall, it's going to depend upon what the quality of soil is. So if I have soil and soil at different levels, I could create a single value for the soil porosity, or I could create the value for soil porosity at different levels. So I could make the model more precise or more approximate. And depending upon if I make it more precise, it's going to be more complicated. It will need more data to calibrate. If I make it more simplified, more aggregated, it's going to have biases that can never be handled. So there's always, if you're trying to model a system, there's always going to be the scale accuracy trade-off that you have to deal with. And oftentimes, some parts of the physics just may be completely missing because you cannot model them. So as a result, your model could be biased. But the bigger problem is that no matter what model you have, there often are parameters that have to be calibrated using observations. And if you have very few observations and a lot of parameters, you can easily overfit. And the environmental sciences, they call this a problem of equifinality. That is, your model, two sets of model parameters that are completely different realities could give you the same error. That means they both look okay, but for completely wrong reasons. Okay? The biggest problem that people face in environmental sciences, and some of it might be applied to your domain as well, is that even though you use observations to calibrate the models, but the traditional modeling framework makes very inefficient use of the observations. And this is what I mean by this. Let's say there's a hydrological basin, there's a river area that you're trying to model, how it responds to the rainfall and other things. If you collect a lot of data about that basin, it's easy for you to build more and more precise physical models because you have a lot of data. You can calibrate different components of it. But if you go from a data-rich region to a data-sparse region, you have to start all over again. That means you have to collect more and more data again from scratch, right? So this is a very inefficient way of using observation. There is no methodology. There is no way for you to use data from highly observed regions and help you the modeling in places where there is no data or very little data. So these are the issues that you face with a process-based model. Okay? And of course, with machine learning, there are other issues because not only they have no physics, which means they can only find patterns in the data that you have. That means there's no way you can extrapolate to scenarios that have never been seen, and you need a lot of observations. So this methodology in which you combine the information in the scientific models and the machine learning together has the potential to provide high predictive power with very few observations, generalize to scenarios that have never been seen before, produce results that are consistent, and then leverage, and the last part is extremely important, the leverage information from highly observed entities to provide high quality predictions in unobserved regions. So these are sort of the promises, the potential promises of bringing the two methodologies together. And this last part is sort of described here in this caricature. Again, it may apply in scenarios beyond environmental sciences. Here you have this green region, we have a bunch of entities for which you have a lot of data. So the entities could be rivers, could be lakes, could be farms. for which you have collected a lot of data and for the past. And then and for which you have both the data about the drivers and the response. Generally, the drivers come for free in environmental sciences. But if you go into the future, you're trying to make predictions. If you're a hydrologist who's trying to tell you about the flood warning, they need to know, they know about the past, but they're trying to improve prediction into the future. So being able to predict into the future is important. So this is one thing you like to do. But then you may also be interested in going to entities that have never been seen before, for which you have no data or very little data. So you have a lot of data for potentially a lot of data for green entity in the green areas. Yellow areas, you're trying to improve prediction, and then the pink area, you're going completely both out of space and out of time. So all of these areas can be of interest, and it turns out that the machine learning combined with scientific knowledge can actually do a very good job of both of these extrapolations, much better than any of these methodologies alone. And being able to, these extrapolations are also at the center of building foundation models. So generally what happens is that in the green area is where you build the foundation model, and then you sort of revise and refine it for applications in the future. So I have only a couple of minutes left now, so I am just going to give you a very high-level overview of how some of these methodologies in the context of environmental sciences have enabled us to build results that are sometimes global scales and significantly better than what anybody could expect by using only pure machine learning model or processes model. On the top left corner, I'm showing you the ability of these methods to build global patterns and data sets. On the top left of the top corner, you see global climate-chemical connections, improved crop maps, the ocean eddy dynamics on a global scale built for the first time using this methodology, and surface water bodies and how they're changing, again, being built using methodologies. They're all unique global data sets that were produced. On the top right quad, you see, again, the work done jointly with USGS, who's responsible for monitoring the health of 185,000 lakes in the US, and they have data only for a small number of them, extensive data for only about a few thousand of them. And what the left half of that quad is sort of showing you is that for the lakes for which they had a lot of data, we demonstrated that this ability to combine knowledge, scientific knowledge, and machine learning together is able to generalize to scenarios unseen far, far better than either machine learning would do or the process model would do. And on the right side, what you're seeing here is for the first time, a temperature dynamics of all of the 186,000 lakes was built using the methodology that I explained to you. You learn from the highly observed areas and go to areas that are unobserved or very poorly observed, because they have data only for about 8,000 lakes in the whole country. And this methodology was built to sort of say, look, now you have data for all the lakes in the US and at a pretty decent quality. On the bottom left here, you're seeing being able to improve the modeling of the stream flow, the hydrology forecasting, and here the key objective is being able to assimilate the data in real time. And what you can see here is the stars are the observations, the stars are the flood levels into the future. You can sort of see the flood level going up and coming down. And the three different colors are showing you the pure process prediction, pure machine learning prediction. And the best one, the blue one, is actually matching 7 days into the future what's happening and what's being predicted. And on the bottom right corner is what you're seeing here is a methodology that's being built to support a framework for turning agriculture from highly carbon intensive to potentially a carbon negative by incentivizing farmers to change their management practices so they can be paid for the change in practices, so revitalizing rural economy, and again also bring help to the environment. So there are all sorts of things that are again made possible by a combination. Again, a lot of them are global products, and nearly everything is sort of work being done for the first time. So with that, let me just, okay, let's see. Yeah, so then the last slide is how can this paradigm of scientific machine learning or the scientific knowledge-guided machine learning turbocharge the generative AI revolution. And on the left side of the slide that you see here is the innovation that have happened in generative AI. Representational learning I mentioned earlier, self-supervision, again, which is all about finding regularities in ways that context-sensitive learning, transformers, and so forth. And there are all the methods that you see in existing methods are driven by the needs of computer vision language modeling domains. And there are the nature of the data in scientific community is so different. And if you go from materials design to being able to design the different kind of structure, they're all very different kind of problem than people solve in vision and languages. And there are different kinds of regularities that you can look for, the different kind of laws that you can look for. So you can completely change the way you're doing self-supervision or building context-sensitive architectures that could bring then new directions in AI that could eventually help us explain some of the issues that we face with the traditional AI, like hallucinations and such. Right? So with that, let me, this is just a little bit more deep dive into how a foundation model for geosciences could be built using the scientific knowledge. Since I'm out of time, I'm going to skip this one. Let me just finish here with these remarks that advances in AI are opening up new frontiers for scientific discovery that go beyond the traditional paradigm of physics-based modeling. There's no question that new directions exist, and anybody would be remiss if they're not leveraging these directions. But building reliable, generalizable, interpretable models require integrating scientific knowledge into this data-driven method. Unless you do that, you won't be able to use these models in ways that you like to use them. And fusion of scientific knowledge into machine learning is poised to drive the next revolution in AI and transforming how we model, predict, and discover. And then the path forward lies in uniting scientific rigor with the flexibility of AI, bringing together both worlds to accelerate discovery. So with that, I'm going to stop and like to thank my team members, acknowledge my grants, and my collaborators around the world. Thank you.
It's a very nice lecture. So we have time for a few questions. Are there any questions from the audience? So I could maybe start with a question. I was curious. I mean, presumably you work with hydrologists and environmental scientists and who are really embedded in the domain. How receptive are they to AI/ML methods? Are they kind of very much looking to get on board, or is there some skepticism from the actual domain scientists? Can you talk a little bit about that?
Absolutely, absolutely. And again, I'm talking about this collaboration that started about 10 years ago. And again, in any community, it's always hard to sort of look at these black box methods and see how they would work. But because we come to them as a partners as opposed to, here is my method, give me your data, we have had much better reception. And again, the proof is in the pudding. If you're able to create something that they could not do before, they're much more receptive to the results. But it has been a great journey. And of course, again, we learn a lot from these collaborations, and we feel that they learn as well. So it's a joint collaborative research venture.
Thank you. Last call for questions from the audience. Okay, I think we're actually right at time here.
You're right on time.
1 minute over. So thank you for coming. I hope you enjoyed the rest of the meeting. I hope to see you around the conference.